Hello and welcome. Today we're going to dive deep into the very heart of how our universe works. We're talking about energy. We're going to deconstruct its fundamental principles, starting with the unbreakable laws that govern it, and then see how those laws play out in the technologies that power our entire world. Let's get started.
So, I want to kick things off with a big question for you. Out of every single principle, every equation we have to describe reality, what do you think is the single most important, the most universal rule of them all? Just let that question sit in the back of your mind for a minute.
All right, in this first section, we are going to answer that question. We're going to establish the foundational law of energy. And trust me, this is a principle that everything else we talk about today is going to build upon.
Now, before we can state the rule, we have to be really clear on our terms. So what is energy? In physics, the formal definition is the capacity to do work. Now, you can't hold it in your hand, it's not a tangible substance, but you see its effects everywhere, from a car moving down the street to the chemical reactions happening in your own cells. At its absolute core, energy is what allows things to change. It's the capacity to make something happen.
And here it is. This is the answer to that big opening question. The single most important rule is the law of conservation of energy. And this principle is absolute. The total amount of energy inside a closed system is constant. It never, ever changes. You don't lose energy, it just gets converted from one type to another.
Okay, I know what you might be thinking. This can feel a little counterintuitive, right? I mean, think about an old-school incandescent light bulb. Its whole job is to make light, but man, does it get hot. That heat feels like wasted energy. So if energy is being wasted, isn't that just a way of saying it's being destroyed?
Nope. And that's the beauty of this law. That heat energy, the thermal energy, it hasn't been destroyed at all. It's just been transformed into a form that isn't very useful for the bulb's main job, which is making light. If you could actually measure the energy coming off as light and add it to the energy coming off as heat, their total would perfectly match the amount of electrical energy you put in. The law holds up. It's inviolable.
So if energy is never lost, but it's always being transformed, the next logical question is, well, what are the different forms it can take? Let's dig into the fundamental types of energy.
We can pretty much group all forms of energy into two main categories. First up, you've got potential energy. This is stored energy, energy that's just waiting to do something. Think of the chemical energy packed into a battery, or the gravitational potential of a boulder sitting at the top of a hill. And on the other side, you have kinetic energy. That's the energy of motion. A car driving on the highway, that's kinetic energy. Even heat, thermal energy, is just the kinetic energy of tiny molecules vibrating back and forth.
Let's trace this in a real-world example. A solar-powered scooter is perfect. So, follow the energy. First, you have radiant energy from the sun hitting a solar panel. That panel converts it into electrical energy. Then that electricity is used to charge a battery where it's stored as chemical potential energy. When you're ready to ride, the battery converts it back into electrical energy for the motor, and finally the motor transforms it into the kinetic energy that actually moves you down the street. See? It's a whole cascade of transformations, and every single step follows that law of conservation.
Okay, so we've established that energy transforms, often in these long, complex chains. This brings up a really critical question for any physicist or engineer. How do we actually track this? How do we measure how good a device is at converting the energy we put in into the useful work we want to get out?
And the concept we use for that is called efficiency. The idea is actually pretty simple. It's just a ratio. You take the useful energy you get out, and you divide it by the total energy you put in. Now, a perfect, 100% efficient device doesn't exist in the real world. You always lose some energy to a wasted form like heat or sound. That's actually an unavoidable consequence of the second law of thermodynamics, which basically says things tend toward disorder.
Let's make this concrete. Imagine a hairdryer. Let's say it uses 1,200 joules of electrical energy. That's our standard unit for energy. Now its useful output, the hot air for drying hair, measures 720 joules. So we just plug that into our formula. 720 divided by 1,200. That gives us 0.6, or 60%. So the hairdryer is 60% efficient. The other 40%, the other 480 joules, was transformed into other things, like the noise of the fan and the kinetic energy of the blowing air.
Now, to really see this energy flow, we have this fantastic tool called a Sankey diagram. It's basically a flowchart where the width of the arrows is proportional to the amount of energy. So you'll have this one thick arrow showing all the energy going in, and then it splits into thinner arrows showing where all that energy goes, some to useful work,
some to waste. It gives you this immediate, intuitive picture of efficiency and conservation in action.
So now that we have the fundamentals down, let's zoom in on the most important energy carrier for our modern world, electricity. And notice I said carrier, not source. Electricity is the incredibly versatile medium we use to move and use energy to power just about everything.
And electricity really comes in two main flavors, AC and DC. The big difference is just the direction the electrons are flowing. In direct current, or DC, they flow in one steady direction. That's what you get from a battery. In alternating current, or AC, the flow actually reverses direction back and forth, periodically. Now, AC is what we use for our power grids, and that's because it won the war of the currents way back when. Its voltage can be easily stepped up and down with transformers, which makes it way more efficient for sending power over long distances.
So where does all this AC electricity come from? The magic happens inside a generator. And the principle is pretty much universal, whether you're using wind, water, or steam. Some moving fluid spins a turbine. That turbine turns a shaft, which is connected to a huge magnet inside a big coil of wire. And when you spin a magnet inside a coil of wire, it induces a flow of electrons. That phenomenon is called electromagnetic induction. And it's this incredibly elegant principle that lets us convert massive amounts of mechanical energy into the electrical energy that powers our world. So, with this whole foundation in physics, we can now turn to some of the most critical questions facing our society. Because how we choose to create that initial motion to spin our turbines, well, it has profound consequences for our planet. Our energy sources really fall into two big camps. You've got your non-renewables, things like coal, oil, and natural gas. These are finite resources. Once we use them, they're gone. And as we know, they're a major source of greenhouse gas emissions. Then you have renewables. These are sources that are naturally replenished, like the sun and the wind, and they operate with very little to no emissions.
And the difference in environmental impact between these two is, well, it's staggering. Take a look at this comparison of the total life cycle emissions for coal versus solar power. That means from manufacturing all the way through operation. The data here shows that solar power's emissions are about 23 times lower than coal's. That huge difference in what we call externalities is really at the center of our global debate about energy policy.
So this leads to a pretty obvious question, right? If the choice is so clear from an environmental standpoint, what's holding us back? Why haven't we just switched everything over? What's the core challenge with renewable energy?
The main challenge for sources like solar and wind is something called intermittency. The sun doesn't always shine, and the wind doesn't always blow. Their output isn't constant. The leading technological solution to this problem is large-scale energy storage, mostly in the form of huge grid-scale batteries. Their whole job is to separate when energy is made from when it's used. You store up all the extra power when the sun is high in the sky, and then you release it later during peak demand or overnight. They make the grid more resilient, they can lower costs, and they are the key to integrating much more clean energy.
But of course, this solution has its own set of challenges. The biggest hurdles right now are the massive upfront cost to build these things and the fact that they have a limited lifespan. They'll eventually need to be replaced. And on top of that, just like any other energy conversion, the process of charging and discharging a battery isn't perfectly efficient. You always lose a little bit of energy as waste heat. It's that same unbreakable physical law we talked about at the very beginning.
And that brings us right back to where we started. The fundamental law of the universe is that energy is never created or destroyed. It can only be transformed. The physics is set in stone. So the real question, the one that is going to define our future, isn't a physics question. It's a human one. Given everything we know, which transformations will we choose to power our world?